Hello, everyone. My name is Elena Reyes from the Passive House Institute, and I'm here today with Melissa Furukawa from Peel Passive House Consulting. We are going to talk to you about a new approach that we developed that relates to primary energy in large multifamily buildings. So basically what we're going to show you is how density relates to the primary energy demand in residential buildings and how we developed a methodology to set a target that takes into account the different end uses in the buildings and then how this translates into a primary energy demand. Afterwards, we'll show you how this exemption is being implemented, and Melissa will show you this through several examples of projects that are currently undergoing certification. And then finally, we'll tell you a bit about the next steps that will happen with this tool. So why do we need an end-use target? Basically, we've been having more and more larger residential projects, but at the same time, these projects have smaller living space, so smaller dwelling units, and they also have additional energy uses. If we take a look at a single family house, and for example, the energy that we need for the appliances, the domestic hot water, and ventilation would be around 33 kilowatt hours per square meter per year. By the way, a small parenthesis, I will be talking in terms of international units, but for your reference, there will also be the numbers in brackets in IP units. So going back to the single family home, it has around 33 kilowatt hours per square meter per year. If we take a similar single family home, but slightly larger, then the specific energy demand would be lower, around 27 kilowatt hours per square meter per year. And that's what density does to the primary energy demand of projects. So take this dwelling unit and then put it in a multifamily project. What will happen is that you have on top of these 33 kilowatt hours per square meter, additional uses like circulation areas, storage rooms, lobbies, elevators, and so on, and of course, more equipment to serve these multifamily projects. So this is what we need to take into account for the revised primary energy demand limit. Actually, the criteria, the passive house criteria already states or foresees an exemption. So if you have extremely high electricity demand in a project, then you can apply for it. But in this case, it's defined on so we review every project to then define a new limit. So what we wanted to do is then to have a standardized approach that would allow us to have project-specific primary energy requirements, but at the same time that would be straightforward and easily applicable by all users. So we did this through a project that was administered by ZEBx and then with funding of the City of Vancouver, Natural Resources Canada, and the BC Ministry of Energy, Mines and Petroleum Resources. The main outcome of this project was an Excel tool. And this Excel tool can be linked to the PHPP file and then gives automatically an adjusted primary energy limit for the project. The tool was released last year in September. And then as a first step, it is also applicable only to residential projects, but the plan is that this is then applicable for other uses. And residential for the project means that we already have a fixed set of parameters that we use for the calculation of the energy balance of the building. It's not only the comfort range that we use for passive houses, but we also have already standard calculations for the occupancy and the internal heat gains. And residential buildings are used 24/7. Along with this, we already have standard values for appliances, and we have recommendations for ventilation rates and a fixed domestic hot water demand of 25 liters per person per day. So once we take these fixed parameters and we put them together with the other energy uses of the building, then it's quite easy to then have a revised primary energy demand. Again, so for most of the uses, we have recommended values, and for dehumidification, cooling, and heating, we then base our limits on the criteria that we already have. In order to combine this or to give like a bar for the efficiency that we need to achieve with the building, then we combine this with efficiency factors that depend on the equipment that we use. And then we take the primary energy factors being PE or PER, and then that's how we obtain the final primary energy demand for the entire project. If we combine this with density, this is how it would look like. So taking a look at the primary energy demand in relation to density, what we see is, for example, here, we have the smallest dwelling units on the left, and then it goes to the right until the largest ones. So what we see is that the PER demand for heating and cooling is fixed, and then the adjustment comes for the other energy uses, for ventilation, domestic hot water, and household electricity. So these are the density-based targets. And then we also have an additional allowance if the project is a multifamily project that takes into account, as mentioned, elevators, common areas, and so on. Because we have different climate zones, then it is the tool also considers the additional cooling and the humidification demand in very, very different climate conditions. So for example, this would be one where the total cooling and the humidification demand would be around 42 kilowatt hours per square meter per year. So in order to verify these targets, we took a look at around 34 projects in different climatic conditions, and then also considering not only single family homes, but also low-rise and high-rise projects. And we made sure that also the dwelling sizes were different. From the results of the projects, we were able to see that most of them actually are able to fulfill the primary energy criteria with the revised target. What you see in the graph is the gray rectangles are the results for each of the projects. The dotted line with different colors is the revised target. The color represents the different climate zone. And the gray line on top of it is the revised target when you have compensation through renewable energy. So there were 5 projects where the primary energy target was above. So the primary energy target was below what the project had, and these cases were those where the domestic hot water distribution losses were very high, or where the projects used direct electricity or boiler as a heat source. So it is important to note that these projects, however, still fulfill the criteria through the traditional primary energy scheme. And so the tool will also include the calculation with the primary energy. The green arrow represents the line where actually the tool gives us a limit that is below the 60 that is defined in the criteria. So in those cases, the projects can still be certified with the traditional 60 limit. So how we implemented this exemption, or how this can be implemented in the different projects, is basically through a tool. The tool is an Excel file that can be linked to the PHPP. You would need a PHPP that is 9.6 or newer. And because this was just released last year, then the tool is on a test phase. And if you want to use it, then you need to contact a certifier. So what I'm going to do now is to show you a bit how the tool looks like. And so one of the most important things, or one of the things that we wanted to do with the tool, is that it actually can work from the beginning. So the design teams can have a very good idea of what the target would be, even if they're at the beginning of the design stage. So all you need to do is to open an empty PHPP, which I have to the right of my screen, and then open the tool. The first thing that we will do is just enter some information into the tool about the project. So all you need is the project location and a rough estimate of the treated floor area and the number of dwelling units. So we go to PHPP and we select the country where the project is located. In this case, I'm going to use the first example that Melissa would be explaining, so that you can compare the limit when there's an empty PHPP or when there is already more information about the project. So the project is in Canada. Then we need to enter the number of dwelling units. In this case, the project has 42 dwelling units. Then we need to go to the climate worksheet and select the climate. In this case, the project is located in Ottawa. So I first look for Canada and then select the location. If you already have the altitude of the project, then it's good that you put it, because as you know, the climate data will have some adaptation. If you don't have it, then you can just leave this cell empty. Then we go to the areas worksheet, and what we need here is, as mentioned, a rough estimate of the treated floor area, which in this case is 2,000, around 2,000 square meters, and then the building footprint. So once we have this information in PHPP, we no longer need the PHPP, but it needs to be open so that the tool works. In the tool, we go to the worksheet residential. And what we need to do is to write the name of the PHPP file that we are using. In this case, it's the empty PHPP. It is important that the name has to include the extension of the file for the links to work correctly. And then you select the version. So once you select the version, you'll be able to see here in the project information exactly the same data that I just entered in PHPP. And then we scroll down, and we can already see what the new target for the project would be. In this case, it's around 76 kilowatt hours per square meter per year. And for the primary energy demand, 142.5. You can also scroll down, and then it will show you how the target was calculated per energy use. The categories are exactly the same as the ones in the PER worksheet in PHPP. So first you have heating, then you have cooling and dehumidification, domestic hot water generation, electricity, and finally gas for cooking and drying. If you want to know the detailed calculation, you can also keep scrolling down, and then all the calculations of the different targets are shown here. Of course, at the moment, because I'm using an empty PHPP, there are no results for the project, but Melissa will show you several ones. And then if you keep going to the right, then you can see the different energy uses in the form of a graph. Once Melissa shows you the examples, and you can see how you can easily compare these to your own project. Another thing that you can also use is this section here for additional information. For multifamily projects, if they have common areas or an elevator, then as mentioned, the target would be a bit higher. So in this case, this project actually has a common area of around 600 square meters, and it has an elevator. So you can see now that the target is slightly higher. So it was before around 75, and now it's around 83 kilowatt hours per square meter per year.
Thank you, Elena. So now we're going to go through some project examples. The first project we'll call Project A is a high-density mixed-use building, around 40 meters squared or 430 square feet on average per suite. This is a mixed-use building which has a medical clinic and community space on the ground floor and 3 floors of seniors apartments above. The project is located in Ottawa, Ontario. As Elena described earlier, it's 42 units. It has a TFA of around 2,000 square meters or 24,000 square feet, with a common area space of 591 square meters or 6,000 square feet. The heating for this building is provided by electric duct heaters, and the cooling is provided by a chiller. And the domestic hot water is provided by a natural gas condensing boiler. So now we'll look at the PER tool for this project. So we have the PHPP open. So we have the tool. We just have to input the PHPP name with the correct extension, the PHP version, the common area, and indicate that there is an elevator. And so now we can see the project data is pulled from that PHPP file. The target values are shown here on the left. So we have a PER demand target of 82.9 and a PE demand target of 157.2. So our project actually has a PER of 102.8. So we're not meeting that this new PER demand, but however, we are meeting the PE demand we're at 147.8. And we'll go through why this is so high, but essentially it's because the domestic hot water is using natural gas. So if we scroll down, we can see the different end uses that make up the PER and the PE calculation. So the first one is heating. So our target value is 16, where our project is at 16.2 for the PER. So we're almost meeting the heating demand, the PER demand. The PE target is 28.6, whereas the project is at 33.1. So we're just a little bit over, and that's because of the higher PE factor for electricity. The project again is using direct electricity, so actually the efficiency factor is low, 1, but the space heating demand is low, 8.6, compared to the target of 15. So that's why it's kind of the low space heating demand is compensating for the higher or the lower efficiency of a direct electric versus the tool assumes that you're using a heat pump with a COP of 2. The cooling dehumidification, the PER target is 11.1, the project is at 4.6, the PE target is 20.6, the project is at 9.5, so we're fine on both of those marks. That's essentially because the cooling demand is very low due to the climate in Ottawa. There's very little need for any cooling, or the cooling demand is just very low there. Next, we have domestic hot water. So the PER target for this project is 19.6, whereas the project is actually at 49.9. And this is largely because of the high PER factor for natural gas and also the efficiency. The tool assumes an efficiency of, well, a COP of 2, and in the project we're using domestic hot water condensing boiler. So it's essentially efficiency of a little bit less than 1. So that's why the PER for this project is so high for domestic hot water. But then when we look at PE, it's a much more on par with the target. So the target is 34.8, whereas the project is at 32.5. So we are meeting that component of it. Next, we have electricity. So this is lighting, elevators, appliances. The target is calculated at 35.2, whereas the project is at 32.1. So we're meeting that for the PER, and then also similarly, we're a little bit lower for the PE as well. If we look at the different line items, the one that stands out is on row 63. So this is the elevator. So the tool calculates a PER of 1, whereas the project is 11.9. So that really indicates that either, that like a really poor elevator was chosen. This project is actually using some on-site data, which still needs to be verified. So this is potentially questionable, but it could also just be a very inefficient elevator. And then we have the other factors, which is like lighting and things for the common areas, and then electricity for pumps and things. There's no gas for cooking or drying in this project, so there's no factor for that. If we scroll over to the right, there is a summary of the target and project final energy, PER and PE, and then they also give the project CO2 in kilograms of equivalent CO2. So you can see this is just a breakdown summary of all those different components that we went through, and you can see the totals at the bottom. And there's also a graph. There's also a graph below that, which shows just in graphical form that chart. So we can see the target final energy versus the project final energy. Large big things that pop up are this is orange is the domestic hot water. So the project is using has a much higher domestic hot water, and this green here is that elevator. And that shows up too in the PER. So we have a much larger contribution to domestic hot water in the PER, and also this large chunk for the elevator, which is really why the project PER is much higher than the target PER. Then if we look at the PE, you can see the domestic hot water is more on balance. We still have a large contribution here from that elevator. But overall, the project PE is lower than the target PE. So the next project we're going to look at is project B. This is a medium density multi-unit family house with around an average of 66 meters squared per suite. This is a community housing development with community space and some building storage and kind of admin spaces on as well on the ground floor and basement. The project is located in Windsor, Ontario. It has 145 units with a TFA of 9,869 meters squared and 365 meters squared of common areas. The heating and cooling for this building are fan coil units on a VRF system. And again, the domestic hot water, it is a natural gas condensing boiler. So if we look at the PR tool for this project, again, we input the PHPP file name and input these additional informations here. The target PER for this project is 72.7, whereas the project is at 85.3. So we're not meeting the PER demand. However, we are meeting the PE demand at a target of 137.2, and the project is at 115.2. Again, if we go through the different components, we can see that, well, the heating, both the PER and PE are much lower than the target value. And this is, again, because the space heating demand for this project is quite low, and they're using VRF systems, so the efficiency is quite high. And you can see the final energy for the space heating is quite low, 3.6. That considers the efficiency of the system and the space heating demand. So for cooling, again, the project is in Windsor, so the cooling demand generally, because of the climate, is quite low. So we're meeting both the PER and the PE demand for this project. And the domestic hot water is where, again, we see a high discrepancy. The target is 17.2 for this project, whereas the PER for this project is 43.1. And this is because the project is using a natural gas condensing boiler, which has a large PER factor and a low efficiency factor than what's assumed in the tool. But we're just a little bit over on the PE at 31.5 versus the target of 30.3. And then for the electricity, we have a PER target of 28, whereas the project is at 24.5, and a PE target of 58.3, whereas the project has 53.2. So meeting both of those. And then, yeah, you can see the breakdown here. This elevator is still a little bit higher than what is assumed in PHPP, but more on par than compared to the other project. And then this project also it's still in design phase, so they're not yet sure what kind of dryers they'll use. So they have, to be conservative, put in an estimate for gas dryers. So that's what this is accounting for here. So again, if we scroll to the right, we can see a summary of all of those different components, the heating, cooling, etc. And that's how they get to the target values. And then the graphs. So again, for the PER, you can see there's a high contribution from the domestic hot water, which is really pushing the PER for the project over the target value. You can see that the other components like the space heating is much lower. The household electricity is much lower. This is the gas from the dryer, that yellowish bar. But then we move to PE, the domestic hot water is more on par. Yeah, so if we look at the project, the target and the project PE, the domestic hot water is more on par. The spacing demand is much lower. So overall, we have we are lower than the project is lower than the target. Okay, next I'm going to talk about a few projects with lower densities. So I'll go more into detail on this project C, which is a multi-family residential building. On average, the suites are quite large. They're 190 square meters. There's 44 units. The location is in Toronto for all of these projects. The other two that we're going to look at just less in detail are two single-family home projects. So there's just one unit, and we just going to look at that to see how the PER target would be calculated for a larger, a lower density project. All of these projects use heat pumps for cooling, heating, and domestic hot water. So this is an example just to show you that, you know, the PER demand can be used. The other two, we're using the PE demand largely because they're using natural gas. This project is using all electricity heat pumps. So the PER target is 40.7 and the PER for the project is 39.9. So we are meeting the PER demand. And actually the PE for the project is higher than the PE demand. So this project will be looking at certification under the PER. You can see that the heating is just slightly lower for the project at 11.9 versus the target of 12.1. And the PE for the heating is actually larger in the project than it is for the target. The cooling is just slightly lower than the PER target of 9.4. The project is at 8.1. And the PE is also slightly lower at 15.5 versus the target of 16.2. The domestic hot water in this example is very good at 6.7 for the PER compared to the target of 9.8. And again, this is because they're using a heat pump for domestic hot water. So the efficiency is high, and the PER factor is also low because they're using electricity. And the electricity for household appliances and other uses is also calculated at 9.4, and the project is slightly higher at 13.2. And there's no gas in this project. So again, if there's the table to the right, which summarizes everything, and the graph also to the right. So we can see that the PER is just slightly under for the project, whereas the PER is slightly higher due to the various different components, mainly the space heating demand and the household electricity. But in this case, the project would be certified under the PER target. So this graph just shows all of those examples. So we have, oops, sorry, I'm going to start again. So this graph shows the PER versus the average suite size for those 3 examples that we went into detail, and then also 2 more examples. The orange dots show the target PER calculated by the tool, and the blue dot shows the project PER calculated by PHPP. And the dashed line is just indicating that classic PER criteria of 60 kilowatt hours per meter square per year. So going in order, A, B, and C are the projects that we looked at, from kind of high density to low density. And then these two other examples are single family home examples. So this is just to show that the PER tool is actually more stringent than the classic PER target. So the classic PER target is 60, whereas for these projects, you can see that the target PER calculated, these orange dots, are much lower than that at like 50 and 40 kilowatt hours per meter square per year. So all of these projects would meet the C and the two single family homes projects would meet either the PER target or the classic PER target of 60. In this case, since the target PER is less than the PER criteria, as Elena said, like you could still use the 60 criteria. For these projects, actually, the project PER is higher than the target PER, so they wouldn't be certifiable under the PER. But if we look at PE versus the suite size for those same projects, you can see that A and B are meeting the PE target. So the project PE is actually lower than the target PE calculated by the tool. And again, this is the classic PE target set, which is 120 kilowatt hours per meter square per year. Okay, and now I'm going to hand it back over to Elena to talk about implementing the allowance.
Thank you, Melissa. So for this last part, what I'm going to do is to talk to you about some additional tips about how to implement the allowance for the different projects, and then go through some of the conclusions and lessons learned that we had through the study, and to show you or inform you a bit about the next steps that we want to have with this tool. So first of all, keep in mind that we've been talking mainly about projects that are residential, but it can be the case that these projects are also mixed use. So for example, we would have projects with amenities that are quite different to a residential use if they have a gym or an inside pool or several areas that are shared by the users, or we can have a fully mixed use building where there are commercial areas on the bottom. So for these cases, we would have a mix of the calculated allowance. So basically the calculated allowance would work for what you see in the slide as the blue areas, which would be the residential area. And then you would have to calculate the orange and the green areas separately with the traditional limit of 60 kilowatt hours for the PER scheme or 120 for the PE scheme. And then at the end, what you would do is an area weighted average of the two or the different zones to get to the final target. The tool already has a worksheet where you can actually do this in a very easy way. So you have the residential project linked to the tool, and then you just enter the main results of the non-residential part, and the area weighted average is done automatically. So the tool is also or it's possible to use the tool also if you want to have a passive house plus or premium. So basically how it works is if you have a passive house classic, you can use the 60 or the calculated target in the tool. If it's a passive house plus, then you have 45 or the calculated target minus 15. And if it's a premium, then it's a 30 or the calculated target minus 30. This is also automatically done in the tool. Once you select that you want to certify plus or premium, then the results are shown for these classes. The targets for renewable energy renovation remain the same for plus and premium. So what we wanted to achieve, or what we expect to achieve with this tool, is that we have more certainty for the projects from the early stages of the planning process. So as you saw, you can already have like a rough idea of what the target would be, even if you don't have a PHPP of the project yet. And then hopefully we will be able to recognize better the effect of density and the additional energy uses in this type of projects. And hopefully and notably, there will be positive consequences for densely occupied multifamily projects, because they previously struggled to meet the PER criterion. And we will also be able to properly recognize outstanding projects. So these projects that would actually meet the limit would now be recognized, or can be recognized, as plus or premium in some cases, if they also have generation through renewable resources of energy. And probably one of the main takeouts of these tool, or the target, is that, I mean, as Melissa already showed, we have an adjusted target and it increases with density, but the bar is still quite high. So don't forget to just go through, or to start your project with the passive house basics, the envelope, using heat recovery, and so on. And then there's also a huge potential of savings through domestic hot water, mainly by making the distribution system more efficient and reducing the distribution losses. And then once you have these main energy users, then you can go on and then further improve appliances, lighting, elevators, and other equipment. So another thing that we learned through this project is what is the average portion of energy that is used in the different categories in residential buildings. What you see in the graph is the target, what we are using for the project, and then the average of the models that we use for the evaluation. And as mentioned, one of the most important takeaways is that, for example, on average, the projects have around 117% additional energy demand just for the distribution losses. We have had different monitoring projects, and it is possible to have distribution losses of less than 40%, and this is what we would aim as a target. But at the moment, because most of the projects had such high distribution losses, then the target was set to up to 100%. Also, because it is very frequent that projects use boilers or direct electricity sometimes for heating domestic hot water, as Melissa mentioned. For example, in most of her projects, they were using a boiler. Then actually the efficiency factor on average for the projects that we looked at is a bit lower than what we are aiming for. So on average, the projects that we had much, much higher domestic hot water use than what the target is now. Another potential point where the energy demand was much higher was for auxiliary electricity. So this is a point where you can also take a look in your project and see how much energy you can save. In the case of household electricity, once you reduce the energy you need for heating, cooling, and hopefully domestic hot water, then the major contributor to the primary energy demand becomes the household appliances. So this is definitely one point in which you can also save a lot of energy. And so one of the things that we also did in this project was to take a look at how efficient are the appliances that are currently available in the market. So we took a look at appliances, not only in the European Union, so mainly Germany, but also in North America. North America, we took a look at the appliances that we have in Canada and the US. So the first line that you see is the energy demand that we have in a project. Again, we're looking at the dwelling size, to the left, the smaller dwelling size, and to the right, the larger dwelling size. And the line shows you how the energy demand, the specific energy demand, decreases as the dwelling size increases, but it also shows you the potential for energy savings in your project. So this red dotted line, which is actually combined with what is the typical values for products in North America, is where we are now. So this is what you get from PHPP if you use the standard values for appliances. Then we have several additional lines. The next one is So the other one that combines is, again, as mentioned, the typical products in North America. The next one is an average of good products in North America. So these are not the best available, but you can already see that if you use products that are, for example, certified by Energy Star and are better than the ones that are with the maximum energy demand there, then you can already save a lot of energy through that. The blue line here is what is currently typical in the European Union. So you can see already that there's a huge difference in the potential for savings in the two regions, because what is the average in the market right now in Europe is actually what is considered quite efficient already in North America. Then the final green energy line here is what is currently available as the best in Energy Star. And as you can see, the other blue line here, this one is what are considered good appliances in the European Union, but not yet the best. So what is the best available in North America is somewhere around better than the average in the EU, but and quite good compared to the typical values in PHPP, but still not as good as the best available appliances in the European Union. In any way, I think that the main takeaway from this graph is that if you are going to install the appliances in the projects that you're working on, then you definitely should look at having products that are certified and that have an efficiency that is above the average, because there's a lot of savings that can be achieved through this strategy. So additionally, or going back to our graph, then what happens is once you use quite efficient appliances, then this green part that is now the majority or one of the major contributors to the primary energy demand would basically can be reduced to half of what it is right now. So again, the main takeaways here are there's lots of potential of savings through distribution losses in domestic hot water, and then revising whether appliances can be more efficient and much more efficient than the average in the market is. Recommended certified appliances would be the easiest way to guarantee that these are efficient. And yeah, of course, then heating, cooling, dehumidification, and ventilation, these are more or less already reduced to the minimum through the other criteria for passive houses. So to finish up, I just want to show you what we are planning for the next steps for this tool. So we want to extend this so that the calculation can also be done for the other certification programs that we have. So it would also be available soon for EnerFit and PHI low energy buildings. And then this calculation will be integrated into PHPP 10 so that this is also verifiable automatically, and then there would not be an additional file that you have to link to the PHPP. And as mentioned at the beginning, we are also planning to develop a similar approach for other uses, for example, offices or commercial buildings.
Okay, so in conclusion, this PR tool can be used to calculate your target PR or a new target PE, but it can also be used to help you determine where there are areas of improvement. So if your project is not quite meeting the PR or PE demand, all these have already kind of gone through design and they're meeting either the PE or the PER target. But if your project's not quite there, you can use this tool to look at each kind of line item, heating, cooling, domestic hot water, electricity, and see where there's areas of improvement. Like in the first example, there was a really high elevator demand energy, so that these kind of things can be discovered through using this tool. What is kind of expected and where your project is at. there may be some projects where there's a lot of domestic hot water losses due to the design of the circulation system or the storage tank. So these kind of things will be kind of evident once you look through all of these different components that make up the PER and the PE target values. So I hope this tool will be helpful for you. It has definitely, as a certifier, it's definitely made my life easier in terms of, projects can really from the beginning know what their PE or PE target will be, instead of waiting kind of later in the game where we would have to liaise with PHI to get a project-specific target. So it makes the certification process much easier for both the consultant and the certifier for high-density multifamily projects. So definitely, if you have a multifamily residential project, contact your certifier early on in the design phase so that you can be really clear about what your target is. And that will help you reach certification.
And that is all from our side. Thank you very much for your attention.